I'm gonna fill a few seconds. Okay, we're happy to have Abdul Zalloum who will talk about strongly coordinated median spaces.
Yeah, sorry, I changed my my original title. I was gonna speak about effective rank rigidity. It's a great paper. You should read it anyway. But I've been talking with Uri. Oh, where is Uri? Okay, you're here. Good. Yeah, and he's interested in something that I've been thinking about. So I changed my title accordingly, and it also relates to the theme of last week. So it's so I think it'll be maybe a bit better. So let's do that. So yeah, this is joined with Petit and Cipriano. Okay, so let's start. So what's the first thing I want to define? So I have in the title a strongly coarse median space. So what's that? So a strongly coarse median space. Let me just tell you, and then I'll write it. So what's a strongly coarse median space? It's just a metric space where every finite set is contained in a bigger set, and this bigger set is quasi-isometric to a cat-zero cube complex. Simple enough. Okay, now the definition is a bit longer. So let me. So what's actually as a strongly coarse median space? Let's say S, following Harry's notation, and maybe with distance d. So it's just a metric space is a metric space with an operator. So with a map mu that goes from S3 to S, such that for every, so it comes with a map from S3 to S, and it comes with a constant E. So and a constant E. So this constant will quantify the coarseness of the definition, but it's uniform, such that every finite set is contained in, so every finite set, maybe I'll call it F, is contained in a bigger set. I'll call it H. And this bigger set is quasi-isometric to a cat-zero cube complex. So which is quasi, we don't do this. Okay, which is AA quasi-isometric to a cat-zero cube complex of uniformly finite dimension. So to a, I'll tell you where A comes from in a second, to a cat-zero cube complex of a uniformly finite dimension, such that the following holds. So such that, okay, so each finite set is contained in a bigger set, and this bigger set is AA quasi-isometric to a cat-zero cube complex. Maybe I'll say via the map. So here is the quasi-isometry. F that goes from Q to H, and I want some conditions to be satisfied. So what is this A? This A is a function of the cardinality of F. It's not a function of F. I don't care about F itself. A depends on how big F is. So it's a function of the cardinality of F. And this quasi-isometry is not any quasi-isometry. It respects the median that you have on Q. So the image of the median of 3 points, A, B, and C, is close. And how close is A close, depending on F? So it's A close to the operator that I have of F of A, F of B, F of C. So this is true for every A, B, C that you have in Q. Okay, and the final thing is that this H is a coarsely median convex set. And how coarsely median convex is uniform. So more formally, number 3 says that for every X and Y that live in H, and for every Z that lives in S, we have the median of X, Y, Z. It lies in the E neighborhood of my set H. Is the definition clear? Yes? Is it too big? Or... Yeah. So the definition of a coarse median, the actual definition of a coarse median, does not involve any metric structure. The definition of a coarse median space is it just says that if you give me any finite set and you close it under the median algebra, then you can approximate this by a Cat0 cube complex. But the point is you don't see what's in between. So for example, if I give you these 3 points in a coarse median space, and you close it under the median, so you just add this point. So let's say this is a hyperbolic space. You take these 3 points and you close it under the median. The definition of a coarse median will just give you a tripod with no information about the distance between the respective points. So x, so let's call this x, this y, this z. X and y and z could be extremely far from each other, but the tripod you get could be at distance. These 2 points are distance 1, 1, 1. The definition of a coarse median does not see any. It does not see in betweenness. This definition sees in betweenness. The cube complex is Q. Yes, yes, yes. So every finite set is contained in a bigger set H. H is supposed to be finite as well. That's right. Yeah. Yeah, it's a subset of S. Did I not say that? Thank you. Yeah, so it's a subset of S. Yes. Other questions? No, this is A. How? Okay, so I have an approximation. The quality of the quasi-isometry and the quality of the median approximation depends on the cardinality of the set A. However, how convex the set is does not. Yes. Yeah. Yes. It's independent of everything. Yes. Yeah. Why else would they write uniformly? What else can it be? Come on, Rob. Okay, so let's go on. So what's the next thing? So okay, so here is okay. So this is the definition. Let me just quickly tell you how we came up with this definition. So this definition, I guess, is due to me, Petit Cipriano, but really what made it interesting, the reason we thought about introducing it is Berstock, Hagen, and Sisto proved that all hierarchically hyperbolic spaces, which includes this list of examples, have this property. Okay. But Cat0 cube complexes are not hierarchically hyperbolic in general, but they also live under this example. This is a theorem due to us. Okay. Well, that's a joke. You're supposed to laugh. Okay. Anyway, so are we good? Yeah. So that's how this definition came about. Yeah. It's the finite dimensional. That's right. Yeah. So the goal of the talk is, well, you'll see what the goal of the talk is. So let's see. So okay, so definition. So a K median. By the way, the dimension of the cube complex, this uniformness, I'm going to call it the dimension of S. It's just a number like 15 or something, right? So maybe I'll write it explicitly. So define the dimension of S is defined to be the max of the dimension of Q, where Q is as in the definition, where Q as before. Okay, so here is the first maybe thing we're gonna play with. So a median, so a K median path. It's a path that respects the median. That's all. So a K median path is a map.
You need to play. I mean, if you change the, you might change the.
I'm insisting that Q is of a uniformly finite dimension. That's my definition.
But the existence of Q is required. Maybe you can change Q. Maybe you can.
You can change Q, right? Yes. You can always find such a Q of a uniform. You can always find such a Q. You can always find. Yeah, you're saying you can add more cubes, but the definition tells you that you can always find such a Q of a uniformly finite dimension that approximates any set. Okay, you guys, but you got it. Okay, just do it. Just do you understand the definition or not? You do. Okay, let's move on. Okay, so a K median path is a median path. So what is it? So a K median path is so it's a map that goes from an interval to your set S. And this map respects the median in the following sense. So such that if A is less than B is less than C, and all of these are elements in I, and you look at the median of alpha A, alpha B, alpha C, then the median of these three things, it's K close to the middle point, alpha of B. So just a picture to keep in mind, a median path is something like this. I have 3 points. So here is maybe X, here is Y, and here is the point in the middle, maybe Z. Being median means that the median of X, Y, Z is coarsely Z. Okay? Questions? Okay, so well, the first observation is that every pair of points in a strongly coarse median space can be connected by a uniform quality K median path. Maybe I should also point out that if you're a cat-zero cube complex, then a path is zero median if and only if it's a geodesic, right? You can see that. Well, reparameterized geodesic to be precise, but that's okay. So, okay. Okay. So this is an inside joke that let's see. So what was I going to say? Right. So so lemma. So every pair of points in a strongly coarse median space, so every xy in a strongly coarse median space are connected by a uniform quality, so by a uniform quality median path, or a uniform quality, I guess, E prime median path, where E prime depends on nothing. It just depends on S. Okay, how do you prove this? Uniform quality. Well, we define the K median path. It's something that depends on K. So uniform quality means you don't depend on K. You're just uniform independently of the points X and Y. How good your median path is, how the coarseness is just uniform.
Means that there exists E prime, such that for each X and Y in X, they are connected by an E prime median path, right?
Yes, that's right.
Step 2 now.
So step 2 is the proof. Yes. So what's the proof? Yeah. So the proof of this. So you just look at your points X and Y. So by the definition, this is a finite set, right? The definition tells us that there is a bigger set, which is H. And this bigger set is quasi-isometric to a cat-zero cube complex, Q. Now, in the cat-zero cube complex, you have X prime and you have Y prime. The quality of this map only depends on the number 2, so it's uniform. It depends on the number 2. So you just take a median geodesic connecting these two, just take an actual combinatorial geodesic connecting these 2 points, and you push it via the map, and you get what you want. Yeah. Yeah. Okay. So right. Good. So from now on, when I say just a median path without a constant, I'll be referring to these median paths. And the reason I'm going to omit the constant is because it's uniform. We don't really need to keep writing it. Okay. Okay. So final definition before we start maybe getting into the real stuff. So a set is said to be K median convex. So here is another definition. So a set Y is said to be K median convex if for any 2 points in Y and any point outside of Y, well, it doesn't have to be outside, for any 2 points in Y and any Z in S, if you look at the median of XYZ, the median of XYZ lives in the K neighborhood of my set Y. Okay, so the K neighborhood of my set Y, I guess big K. Questions so far? Just the definition, just corsifying Elia's course, I guess, is what I'm doing. Okay, so here is a definition. So, okay, so definition. So this is going to be the analog of a wall that Ilya defined. So it's a coarse analog of a wall, and we're going to see lots of applications for this notion. So a curtain is a set. So it's a set H such that if you look at its complement consists of two pieces, H plus and H minus. And these two pieces, so such that each H plus and H minus are E median convex. So H plus and H minus are median convex with a uniform quality constant. Okay, sometimes I will just call these median convex because the constant is uniform. So E median convex. And I want the two half spaces to be far apart. This is similar to what Harry said. You just take two walls at distance at least one. This lets you relate the distance in the actual space to counting the number of these walls, and this will be useful. So and the distance between H plus and H minus is at least 30E. Now, don't dare ask me if that's optimal. So yeah, so okay, so that's what the curtain is. And maybe, yeah, thicken. Well, it's not a thicken. There is no wall to thicken. It's just, yeah, you should think of it as a thickened wall. But no, but you should be careful because a thickened wall looks like this, and these guys could look like this. They could really go arbitrary, and that's the generic picture. Actually, they do get really bad. They get really, you know, yeah. The distance between points in the curtain itself and the corresponding half spaces can be arbitrarily far, unlike a thickened wall. Okay, so maybe here is a first lemma that's gonna help us prove a few things. The first lemma is gonna tell us that in a strongly coarse median space, the distance between 2 points is coarsely the maximal chain of curtains that separate them. So let me maybe first tell you what I mean by separates, and I mean by and what I mean by a chain. It's essentially what Harry said, but so okay, so what do I mean by separate? So definition. So we will say so we will say that H separates two sets A and B if A lives in the positive half space and B lives in the negative half space. And a chain, I'll just be looking at finite chains to make my life simple. So a chain is a collection of curtains such that, so a chain is a set of this form. So maybe I'll write that. So it's a set that looks like H1, H2, up to Hn, such that each Hi separates Hi minus 1 from Hi plus 1, such that Hi separates Hi minus 1 from Hi plus 1. Questions? Notice that this definition of separation, it prevents these curtains from overlapping. The curtains themselves do not overlap, right? Yeah. Someone has a question. Yes.
That strongly coarse median space has NS1 curtain.
Has to say again?
NS1 curtain.
At least one quality?
Curtain.
Oh, we're coming up. Yeah, of course. This is the point. We're gonna show that, right? So this is the point of, right. I mean, you can't, yeah, you make a definition, you show it exists, right? That's the okay, so right. So this is so here is a lemma or a theorem. So this is again PSZ. And the lemma tells you that there is a lot of them. So it tells you that the distance, so for any xy in S, we have the distance between x and y it coarsely agrees, uniformly coarsely, with the cardinality of the maximal or a maximal chain of curtains separating X and Y. So let's see the proof. So the proof is it's due to HHP, which are Hatel, Hoda, and Petit. You can see there is a common author here. And so what happened is that Harry was sick of being a last name. So he chose to start writing papers with us to become a first name. So, okay, so what's the proof? So the proof is quite simple. So the proof is we're going to construct a map. So yeah. That is true. I mean, yeah. That is true. That's the point. We reformulated things in a way, but the proof is due to them. Yeah. So what? Okay, fine. It's due to Zach. Let's go on. So what's the how do you prove such a theorem? So the idea is that we're going to construct a map phi that goes from S to R. And this map is going to send X and Y roughly their distance away to R. And once you do, so we're going to construct the map, and this map will preserve median. So construct phi, and such that phi preserves, or phi preserves medians coarsely. And the distance in R between P of Y and P of X, it coarsely agrees with the distance between X and Y. So let me first just convince you that once you have that, you're done. Once you have that, you just take fibers of this map. And the fact that this map is median preserving, it will assure that your fibers are convex. Or that's the key to proving that the fibers are convex. Okay? Yeah, Tuma Hatel is shaking his head. It's like Abdul takes our theorems and makes theorems out of them. So that's well, that's true for this particular thing. So let's so how do you construct a map? Well, you just take your points X and Y. So here is X and here is Y. We know that there is a subset H containing them. And this subset is the image of some cat0 cube complex Q. Okay, and you have F inverse going this way. So I have a corresponding 2 points X prime and Y prime that live here. If I look at X prime and Y prime in the cube complex, you can find, first you find the maximal chain of actual hyperplanes separating them. So, and this gives you a map, maybe I'll call it W. So I get a map from Q to R. You guys agree? Yeah. So I get a map from Q to R. And this map is median preserving, and it sends X and Y roughly their distance away. And the reason it sends them roughly their distance away is because Q is of a uniformly finite dimension. Okay, so I'm not done yet. I just found the map from Q to R. My goal was to find a map from S to R. Well, first you can go from H to Q by the quasi-isometry. So I can start by first doing F inverse and then follow it by W. And this will give me a map from H to R. And this map will send X and Y roughly their distance away. So this is going to give me walls in H. It's not going to give me walls for the full space. And to get walls for the full space, it is a natural map that goes from S to H, which is the median of XY blank, right? If you take the median of XY blank, that's going to put you coarsely in H. Okay, so the final map then is, the final map is F inverse. Well, maybe first I should do the median of XY blank. And then I compose this map with F inverse. And then I compose this map with W. And that gives me a map from, so this map goes from S to R. This map coarsely preserves medians, and it takes X and Y roughly their distance away. Are we happy? Does this answer your question? We have a lot of them. We have too many, actually, is the problem. So good. So let's go to the so we're going to start seeing lots of analogies between actual hyperplanes and these curtains that I defined, which are, yeah, it's I was very surprised. I mean, we did this project about 2 years ago, actually, and every time we write a new theorem, it just, yeah.
Can you tell us why one theorem might be a curtain?
The fibers. You have it, okay.
I know.
Yeah, David doesn't know how the proof goes. Just I and Harry proved this. Okay. All right, I guess English please. Okay, so you just you have a map to R. You can just take I guess I insisted on 30E or something, right? So you just take intervals of length 30E. You look at the pre-image under this map. Now this pre-image, it's not so clear that this pre-image is going to be median convex, but you can always take the convex hull. It's a theorem due to Bodish that you can find the convex hull in finitely many steps. So you might shrink a bit. So once you find the convex hull, this set might become smaller, but you can still assure that there's a definite distance here. Did not want to mention that. And okay, good. So but that's the idea. You just take fibers of this. Okay, so I'm gonna convince you. I'm gonna give you a very convincing argument that these curtains are really very much like hyperplanes. All of the things, well, most of the things I know how to do with hyperplanes, I know how to do with these. So let's maybe start with the following. Lemma. And this is actually not due to HHP, finally. So the lemma is, so a path is median. When I say median, I mean it's K median, but K is uniform. So it is median if and only if it never crosses a hyperplane twice. So it never crosses a hyperplane twice. Oh, sorry, a curtain. But let me first be clear about what I mean by cross twice. So our curtains look weird, right? Our curtains look something like this. And by cross twice, I mean you go here and you go here. Okay, so proof. One direction is obvious. Namely, if you know that your path is median, then you cannot cross a curtain twice. Do you see that? You do not see that. So let me. So here is a curtain. We know that this piece here is E median convex. This piece here is also E median convex by definition. If you have something crossing twice, so this is a median path, which means it's a median path with uniform quality. The median of these 2 points and this point, on one hand, it has to be on this side. On the other hand, because the path is median, it has to be this point. That's a contradiction. Yeah? Are we happy? Say again?
Also, you know that it's a path distance.
Yeah. By definition. Yeah, this is the path distance. Yeah. That leaves them. Yeah, that's right. Yeah, that's where the 30 comes in. Now the converse is slightly trickier, but it's also not really much trickier. So how would you prove the converse? You okay. So what's the assumption for the converse? The assumption is that I don't cross a curtain twice. I want to show that I'm median. So let's take these 3 points along the path, and so the assumption is that I don't cross a curtain twice, right? Suppose for the sake of contradiction, I'm not median. So let's call this point X, this point Y, this point Z. Not being median means the median of X, Y, Z, it's far. Maybe it's here. Well, because it's far, by the previous lemma, there are lots of curtains that separate these 2 points, right? So here is maybe the first one, first fat one, please, Zach. The second fat one, to please, Zach. The third fat one, please, myself. And then, okay, so what can they do? Okay, well, we know that you cannot cross the curtain twice. So you have, at best, you will cross it once. So let's say this happens. Well, if this happens, this is a contradiction because Y and Z are on this side of the curtain, but the median is not. Okay. You can look at the other possibilities, but they all, I mean, there's no other possibilities really. That's the thing. Okay, so okay, so maybe it's time for some theorems. Let me first define or remind you what it means to skewer something. Who remembers the definition of skewering? Raise your hand. You don't remember it, Danny? Okay, so let's see. Good. So no, it's a bit different. I mean, it's of course we have lots of course stuff happening. So skewer is not equivalent to skewer. We have to be careful. So what's the definition of skewering? But it's very similar. So definition. So an element G, in aught S. So what's aught S first? Aught S is all isometries which preserve median. They preserve it on the nose. Okay. Yeah. So an element G in aught S is said to skewer. So skewers a curtain H if there exists a power such that G to the n takes H union H plus and it puts it properly inside H plus. So it is different than what you have seen before, because again we have thickness, so we have to be careful about that. So what I'm saying now is that here is H, here is H plus, and here is H minus. To say that I skewer, it means I move everything here and everything here properly inside H plus. Okay, good. Okay, so maybe I will give one more definition, although I will give it. Okay, so yeah, so let's so what's the definition? Harry gave this in his talk, but I will just remind you anyway. So the definition is that H and K are said to be L separated. This is the source of hyperbolicity that Harry told us about. So they're L separated if whenever you have a chain that crosses both. So you have whenever this is a chain that crosses both of my curtains, crossing both HK, we have that the cardinality of this set is at most L. Questions? Okay, so theorem one. Okay, so what's the first thing that you can prove? So theorem, I will give you the proofs. If Thomas gives me an extra, no, I think I'll be able to get to the proofs. How much time do I have? Oh, 34. We have a lot of time. Good. So okay, so what's the deal? So each strongly. That's a very good question. I just mean touching here. I don't mean penetrating in intersecting. But there will be times if I get to give the proof where I'll be more. Sometimes I'll say strongly cross, where I'll mean like penetrate. Yeah, like because we have thickness, and I'll mean like all four spaces actually meet. So here I just mean touching, meeting. So each right. So each strongly coarse median space S with so it comes to the distance by a symmetric space admits coarsely. Okay, where's the R? Okay, coarsely injective distance d infinity. I'll call it d infinity. Such that d infinity is quasi-isometric to d. So d infinity and d differ by a multiplicative and additive amount, which is uniform, in an equivariant way. So it admits a distance which is quasi-isometric, and every G in not X still acts. So still acts. It's still an isometry on the new metric. Is an isometry. So is an isometry of the lots of horrible things. Okay, so every automorphism of the original. So I have an automorphism of the original set with the original metric. Okay, and this automorphism, it acts on this new metric by isometries still. It's like what happens when you switch the cube complex thing distance from L1 to L infinity. So what's a particular? So I'll tell you how we prove this in a second. But as a corollary of this, you get that if you have a group G that acts properly co-boundedly on a strongly coarse median space, then it must act properly co-boundedly on an injective metric space. Okay. And the way we do it is we apply the machine that Harry spoke about early. And I will tell you what's the main thing that needs to be done in a second. So corollary. If G acts geometrically, and by geometrically I mean properly co-boundedly, not properly cocompactly, and these are different, right? So acts geometrically on S with respect to its original distance, then G acts properly co-boundedly on, properly geometrically. So geometrically on a coarsely injective metric space, which is S the infinity. In particular, it also acts geometrically on an injective metric space by what Hetel told us about, the injective office. Okay, so Harry told you about a procedure that takes in walls and it produces an injective metric space. You remember? The injective metric space you produce is usually much larger. I mean, you throw in all ultra filters, right? The key thing is you can prove that the walls I mentioned, I have shown you satisfy the Hilly property. And if the walls satisfy the Hilly property, it means that these ultra filters that you have, which are a priori fake points, they're actually in the space. They're not going to be exactly in the space. They're going to be at the bounded distance from the space. So from the definition, you can prove that whenever you have a collection of strongly crossing walls, they have to pairwise intersect. So this gives you a coarse Hilly property. Okay, and then from the coarse Hilly property, you get that the original set is dense in the space of ultra filters. That's the idea. Now, okay, so good. Okay, so so next theorem. So the next theorem is the following, and then we'll discuss some proofs, I promise, and we'll discuss some fun things also. Someone told me that every talk should contain at least one proof and at least one joke, and they should not be the same. So let's see. So theorem 2 PSZ. So the theorem is the following. Let S be a strongly coarse median space, and let G act properly on S. Okay, so this is the assumption. The conclusion is the following. So maybe I'll start here. So now is the conclusion. There exists a delta hyperbolic quasi-geodesic metric space. I'm not going to write quasi-geodesic, but I want to emphasize that it's not just a delta hyperbolic with the stupid 4 points condition, because that condition is actually quite weak. So what gives it meaning is the fact that it's a quasi-geodesic thing. So it's a delta hyperbolic metric space. Act. Yeah, exactly. Like take a hyperbolic group, for example. It has a coarse median. You can always assume that the action literally preserves that coarse median because it's a coarse notion. You just pick it and you stick to it. Okay, so there exists a delta hyperbolic metric space Y such that the following are equivalent. So what are the equivalent things? I'll write them here. The one, every Morse element. So Morse is you just think of it as a rank 1 element in a cat zero space. Every Morse element acts loxodromically such that the following are equivalents. No, this, what am I saying? Okay, an element G is Morse, so G is Morse. So G is did I specify where G is? No. Okay, I'm sorry, I missed something. I should just say that G is an odd. Okay, so my bad. I apologize. So there is a such that okay, so such that for every element G in odd S, are you happier? Slightly. With I actually would need one more thing. I want it to be semi-simple. I want to so with the translation length of G is positive, the following are equivalent. So I did miss a lot. Yeah. So G is Morse. 2. So G is Morse. G acts as a WPD loxodromic on this Y. 3, G skewers a pair of L-separated hyperplanes. So G skewers a pair of L-separated curtains. Now, mind you, this theorem applies for the mapping class group and lots of things that you would think don't have hyperplanes, but they actually do. So an element is pseudo-naive if and only if it skewers a pair of no, I did. So G acts for yeah, so G wait. G is in this. Yeah, so G is in G. Yeah, so the reason I have the proper is to assure being WPD. If I didn't assume that G acts properly, I get everything, but I won't know it's a WPD. Wait. Oh my God, this is the most horrible theorem I've ever written. Okay, so G writes properly on S, and then yes, it will also act in Y, right? So yeah, I will write it. Okay, so there exists a delta Euler space. So that's a good point. Y such that that's true, right? I can claim to have written it already, actually, and they just okay. So such that G acts on Y by isometries. Huh? It will act on Y not properly. No. Okay. Yes. Let's get going. Yeah. Okay. So G acts on. Maybe I should have just taken a screenshot from Harry's talk and just put it there. He wrote it better. Okay. So G acts. How much time do I have? Okay. So G acts on Y by isometries. Okay. And for G and G with positive translation length, the following are equivalent. This is a correct sentence now. Okay. With the translation length of G being positive, the following are equivalent. Being Morse is equivalent to acting as a WPD loxodromic on Y, and is equivalent to skewering a pair of L-separated curtains. Now ask questions. Huh?
Where?
G is Morse in the original, so on S. Yeah. So it's rank 1 on S, if and only if it acts loxodromically on this Y. If and only if it skewers a pair of L-separated curtains in S. And L depends on the Morse element, yes. Different Morse elements will act on will skewer possibly worse ill-separated hyperplanes. More questions? Absorb the theorem. It's a great theorem. Think about it. Yeah. No, it means you just take the distance between x, g, and x over n, and you take the limit of that. Yes. Questions? Yeah.
Then why like what the information the L separated?
I don't understand the question. Well, it tells us that you have a pair of ill-separated guys. They're crossed by only finitely many other curtains. We don't know how large this finitely many. In fact, even for a cat zero cube complex with a wait. What's funny? No, Sam. So Sam proved the cool theorem last year. So let me tell you. So he showed that if you have a group G which acts properly he gave an example of a group G that acts properly cocompactly on a cat zero cube complex, and how ill-separated two hyperplanes are goes to infinity. You can find hyperplanes which are 10 separated and not 9 separated, 100 separated and not 99 separated, which is quite surprising. Like you would think a cocompact action would assure that there is a large enough integer where two hyperplanes are either crossed by that many integer or infinitely many, but that doesn't happen. You can have things like a staircase under a cocompact action. Am I right? No, it was a good theorem. So right. So it's not uniform. You can't get a uniform thing. Say again? The L depends. Yeah, that's also right. Yeah. Yes. Okay. Do I have a map from S to Y? S and Y is the same set. You just change the distance, actually. This new hyperbolic space, it's the same trick. You count, and instead of counting all curtains, which would give you the L infinity distance in S, you count the hyperbolic like ones. It's a great trick. Okay, so let me tell you a couple more things about this. So this covers all cat zero cube complexes. By the way, this theorem, if I gave this talk last year around now, this theorem was not known even for cat zero cube complexes. It wasn't known that in the setting of a cat zero cube complex, you can get a single hyperbolic space where all rank 1 elements act lexodromically on. But we proved this for the setting of cat zero spaces in December, which recovers cat zero cube complexes. And now here is another way of getting it. And Stephanie, I think, also has a different way of getting something similar. Yeah. Okay. So now let me just comment on this space Y, here. So this theorem, it applies to right-angled Artin groups, and it applies to mapping class groups. If you're a right-angled Artin group, then this Y is quasi-isometric to the contacted graph of Hagen. And if you're the mapping class group, then this Y is quasi-isometric to the curve graph, which really tells you this is, I don't know, it's kind of cool that you can recover the curve graph from a hyperplane perspective, right? It's a bit cool. So yeah, so good. So what else did I want to say? Yeah.
50 things that sound said that Y is S with a different metric. And if you start with a cube complex, you get the contact graph. That sounds like
What? You get it's quasi-isometric to contact graph. Yeah. It's not exactly the contact graph. Yeah. Okay, so the final thing I wanted to say is the following. Last year I spoke with the Erminsky in Paris, too much information, and he told me that when he and Mazer were proving all the hierarchical structure for the mapping class group, they were always wondering if there is a simple way of getting all of this. If there is just one, they were wondering if there is like, one theorem that encapsulates all of this together. Now, I'm not claiming that this definition is the one thing, but the fact that each pair of points are connected by a median path is exactly the theorem that in the mapping class group, each pair of points are connected by a hierarchy path. Because if your strongly coarse median space happens to be the mapping class group, then a path is median if and only if it's a hierarchy path. 1. 2, the theorem that I proved to you that the distance between X and Y is coarsely the maximal chain of curtains separating them which is due to HHP, you can actually see it as a distance formula. Suppose I don't have this, suppose I don't have the strongly coarse median definition, and I just know that I'm the mapping class group. So maybe I'll lose some people for 2 minutes, but I just want to show how the fact that the distance between 2 points. So at some point I proved that the distance between x and y is coarsely the cardinality of the maximal chain of curtains separating them. I want to reprove this to you just using a mapping class group perspective. And once I do that, you will see that this is really giving you a distance formula. So separating x, y. OK, I hand you a mapping class group. It has a hierarchical structure. You have a pair of points. You project them to each hyperbolic space. And the distance between these 2 points is the sum of the distances in the hyperbolic spaces. How do you get, from this information, how can you get lots of curtains separating x and y? Well, you go to the hyperbolic space, right? So here is your hyperbolic space. Here is one of them. Here is the projection of x. And here is the projection of y. In the hyperbolic space, you can make sense of nearest point projections. So you have fibers here. And you can pull these fibers back to the mapping class group. OK? So this sentence, the distance formula, is an L1 version of this sentence. This is an L infinity version of the distance formula. OK, so another thing which is also interesting, what does it mean for something to not be a hierarchy path? It means that you backtrack in some hyperbolic space. Yeah? But what does it mean to backtrack in some hyperbolic space? It exactly means that you cross a curtain twice, because here is a hyperbolic space, and here's a curtain. Backtracking means that you do something like this and this, right? So a hierarchy path is really exactly what a median path is. So as I mentioned, we proved this theorem about 3 years ago, and then we realized that we weren't really using the median structure that much. I'm talking about this hyperbolicity theorem. The injective theorem does use the median structure a lot, but the fact that there is a universal hyperbolic space with an action, it wasn't really using the median structure that much. All that it was using is that you can separate pairs of points by walls. So the first thing we observed is that you can actually do that for any cat zero space, as Harry mentioned, because there's a natural way to separate 2 points by a wall. You do nearest point projections, you look at pre-images. And then we realized that you actually don't even need a cat zero space. Anytime you have a set, so it turns out that there is a one-to-one correspondence between hyperbolic spaces and sets with walls satisfying certain conditions. So I'd like to spend some time talking about that and how it relates to some work of Bowditch. So the first thing is that there is a one-to-one correspondence between spaces with walls satisfying certain conditions. I will tell you what they are in a bit. And hyperbolic spaces in an equivariant way. So hyperbolic spaces. OK, so how does the correspondence go? So Harry spoke about this for a bit. If I want to go so OK, first off, what do I mean by spaces with walls? So by a space with walls, I mean I have a set S. So let me define what I mean by a space with walls. So a space with walls, I'm defining it as follows. It's simply a set S. So is a set S such that so a set of S with some bipartitions with a collection of bipartitions. So I have a set S with some collection of bipartitions, and I only have the main condition I have is that each pair of points are separated by the cardinality of a maximal chain of walls separating 2 points is finite. You could have uncountably many things separating 2 points, but the chain is finite. So a collection of bipartitions such that for any, so each xy in S are separated by so maybe I'll say it this way, such that for each x and y, if C is a chain, so if C is a chain separating x and y, then the cardinality of C is finite. That's the first condition. The second condition is just that every pair of disjoint walls are L separated. And every pair of disjoint walls are L separated. So if you have a set with these conditions, you can get a hyperbolic metric by just defining the distance between x and y to be 1 plus. I'm writing 1 plus because there could be a kernel, as Harry discussed, namely x and y may not be separated by any wall. You can take care of this in various different ways. You can look at the space of ultrafilters, but maybe the simplest way to do it now is I can just take 1 plus the cardinality of a maximal chain of walls separating x and y, and I declare it to be 0 if and only if x and y are 0. So this turns out to always be a hyperbolic distance. And every hyperbolic space arises in such a fashion. How? You give me a hyperbolic space, you take geodesics, you take pre-images, so you take a geodesic in a hyperbolic space, you take pre-images of nearest point projections, and you can easily prove that the distance between 2 points is coarsely the maximal chain of curtains separating them. In fact, I did prove that to you because hyperbolic spaces are strongly coarse median, right? Okay. Now, the thing that I found very interesting, so we realized this correspondence maybe a year ago, and then 2 years ago, I don't know, at some point in life. And then Nir Lazarovich and Anthony Genevois, they told us that this looks similar to a very nice paper of Bowditch. Okay, so I'll just tell you in words, maybe I'll take 1 more minute. So Bowditch has a paper where he starts with a group G acting on a topological space. And he wants to, so it acts on a topological space with certain conditions. And he wants to show that this group is Gromov hyperbolic. So all he has is a group with some topology. He does not have a distance. And the way he comes up with a distance is by looking at, he looks at open sets in the boundary, and he declares those to be walls. He looks at certain open sets in the boundary, and he declares an open set to be a wall. You're either inside an open set, or you're outside an open set. So these are the walls. And then from walls, he defines distance. Okay. Now, how do you, and then he proves that this distance is hyperbolic. And the way he proves it is by checking this condition. He checks the following. He checks that if you have a chain of open sets, U1 contained in U2, if you have a chain of open sets, U1 contained in U2, contained in U3, etc., and you have another chain of V1 contained in V2, contained in V3, then you can't have lots of crossing of the U chain with the V chain, which is exactly the L separated condition. Now, that was interesting to us because we didn't know about it. But it turned out that I think Bowditch was aware of this correspondence, at least maybe he wasn't, I don't know, okay? But I mean, the ideas are very similar. I think, yeah, probably he was aware of the correspondence. Yeah, I'll stop.
So this is question.
Yeah, it's the effective completion. It's not the first thing to say.
Yes, because it's dense. Because you just can push the coarse median.
Yes. Okay.
Yeah.
I would insert this coarse median space definition and then enhance with these uniform axioms and with the Ajax axioms. You know,
To be honest, I really, first off, you're not going to get an Ajax from this definition because even finite dimensional category comments are not. Okay, and I'm a big fan of HHSs, but I mean, it depends on what you want to do. I mean, this definition seems compact. Let's say it's the best definition in the world. No, I mean, it's not that big. you know, but the point is, you can prove semi-hyperbolic of the mapping question, which was, well, you can prove all these. I don't know. Yeah, it's yeah. What are we doing? I have no idea.
All right, let's think and go again.